everybody, it's Mrs. Hofferberth. Let's talk about ionic bonding. In all bonding, it's the valence electrons that are responsible for what happens. True for ionic, covalent, metallic, it's always your valence electrons that are involved. So we can talk about identifying the valence electrons looking at an orbital diagram, like say for magnesium. And as we talked about before, your valence electrons are those uppermost electrons that are in your 3s and 3p orbitals in this case, since 3 is the last shell that is filled. So this magnesium just has 2 valence electrons. And we can see it with this. Oftentimes you'll see it written as a Lewis dot structure, where each valence electron is represented as a dot. And when we're writing these atomic level Lewis dot structures, we tend to spread out the electrons as much as possible. On the other hand, something like fluorine has 7 valence electrons, and so you would draw its Lewis structure showing those 7 valence electrons. So it's our outermost electrons that are involved in bonding. When we're talking about ionic bonding, what's happening is that we are having oppositely charged ions that result from either the gain of electrons or the loss of electrons in that valence shell. And those oppositely charged ions are going to be attracted to one another. The metals on the left side of the periodic table will form cations. These have only the beginnings of their valence shell filled, and so they'll lose their electrons. And examples of these would be things like magnesium +2, potassium with a +1 charge, aluminum with a +3 charge. Our nonmetals, since their valence shells are almost full, tend to form anions, or ions with a negative charge, things like fluoride, sulfide, oxide, and phosphide. When you go to make a compound with your ionic bonding, you are going to need to make an overall neutral compound. And so we've seen this before when we talked about writing formulas, but we're going to create what's called a formula unit, which is the ratio of ions that are involved to get to a neutral compound. Examples of these formula units would be things like magnesium fluoride, MgF2, where we needed 2 fluorides to balance the charge on the magnesium ion, or Al2S3, where the lowest common multiple for charges is a -6 or +6, and so you need to have that ratio. The reason I'm emphasizing that these are the ratios is that in an ionic compound, the atoms are actually arranged in a crystal lattice, so you don't have a discrete 1 Mg2F2s. No, instead you have billions of atoms in a 3-dimensional repeating pattern. That is what your crystal lattice is. These crystal lattices have a variety of details in terms of how the atoms actually pack together, but the idea is to maximize attractive forces and decrease repulsive forces between the atoms involved in the ionic solid. And so you will always have an overall ratio that matches your formula unit. Now, since these ions are trapped in this crystal lattice, as a solid, they can't move past one another, and so your ionic solids do not conduct electricity. You actually have to separate the ions either by melting it or by dissolving it in an aqueous solution to allow those ions to flow past one another to conduct electricity. Similarly, you can't move the atoms past one another because that interrupts the positive-negative attractions, and as a result, ionic compounds are brittle. We can talk about the attractions and get a feel for how strongly attracted your ions are when we talk about something called the lattice energy. And the lattice energy is the energy needed to actually take 1 mole of an ionic solid and separate it into gaseous ions. Basically, I'm pulling the atoms and the ions completely apart. How much energy does it take? The larger the lattice energy, the stronger the attractive force is. Understanding and predicting relative lattice energies, it's all about Coulomb's law. In general, as the charge on the ions increases, you're going to have a greater force and therefore a greater lattice energy. Similarly, as the distance between the ions increases, you're going to have a smaller force or a smaller lattice energy. And so when we try to measure the distance between the ions, typically we're looking at the sum of their radii. So as the radius on the ions themselves change, you will see a difference in the force. And so you can predict what your lattice energy is actually going to be. Certainly comparing 2 different ionic compounds, you can make some predictions. Actually getting a value for the lattice energy isn't something we can do by experiment because it's really hard to take a ionic solid and actually separate it into gas phase ions. So generally what we do is we take Hess's law and we do what's called a Born-Haber cycle. This is just Hess's law in order to determine lattice energy. I'm going to show you one example for sodium chloride, kind of the classic. So the target is to figure out how to take sodium chloride as a solid into its gas phase ions. So this is your lattice energy. But as I said, that's difficult to do experimentally. So what we're going to do is break this down into steps. The typical process goes as follows. First, we are going to take apart the sodium chloride into its component elements. This is the opposite of the formation equation or the heat of formation for sodium chloride. So we can take our heat of formation, flip the sign. We find that that process takes 411 kilojoules of energy per mole. Okay, next thing, let's take our sodium and let's turn it into a sodium ion. It's going to take us 2 steps. First thing we're going to do is we're going to take solid sodium and we're going to turn it into sodium as a gas. Turns out that this is the heat of formation of gaseous sodium, so we can find that value. Then let's take these gaseous sodium ions and remove an electron. This is the ionization energy. The sodium is now in the form that we need. We need to mess with our chlorine. Right now we have half a mole of diatomic chlorine, but I'm going to need individual chlorine atoms. So I'm going to start by breaking the chlorine-chlorine bond. This is the bond enthalpy of chlorine. And then the last thing I need to do is I need to add an electron to make a chloride ion, which is the electron affinity for chlorine gas. And so after all of these steps are done, we've done the process in a different order, but we've gotten ourselves from our starting material to our target products. And so I can simply sum all of these steps to find the lattice energy. And so the lattice energy for sodium chloride through this rather roundabout process is 788 kilojoules per mole, because lattice energy by definition is for 1 mole of our material. So in sum, when we are talking about bonding, it is the valence electrons that are involved. Ionic bonding specifically, you are looking at the retraction between anions and cations. Metals tend to form cations by losing valence electrons. Nonmetals tend to form anions by gaining valence electrons. These electrons attract to one another, forming a crystal lattice, which is a 3-dimensional repeating pattern of your positive and negative ions. And the attraction of these ions to one another can be understood and can be measured by the lattice energy. The higher the lattice energy, the greater the attraction, and this can be predicted using Coulomb's law and calculated using a Born-Haber cycle or Hess's law on steroids.